In this lecture, we'll talk about applying the chi-squared test to two-way or cross-tabulated tables to test for properties of either homogeneity or independence. So first, let's talk about homogeneity. Homogeneity basically says, are two or more samples similar in distribution? So the null hypothesis is that all samples have a similar distribution, and therefore they would all resemble a total distribution, that is, if you added them all together. So let's consider two samples having elements partitioned into three categories. Now, there's some crazy notation going on here. We've got three categories, two samples A and B, three categories, 1, 2, and 3. And in the cross-tabulation, we see the number of elements that fall into each category per sample. Now, the notation is N and then subscripted with row and column. So N sub row and column. All right. And so that tells how many fall in each category for each sample. All right. Then we sum both the rows and the columns. So we have this crazy thing here with a plus, and that says this is a row total. So we've summed it over all columns. If we sum down, then we put the plus in the first position, and that's a column total. And of course, if we sum the sums, then we've summed over both rows and columns, and that's what's called the grand total. Now, homogeneity says that the pattern in each row should be the pattern of the totals. So then the expected value for any cell would be the prorated portion of the column totals. So we'll look at these and we'll prorate them based on how large each stratum is. And so here's the fraction for the stratum, and here's the column total. And so then the expected value can just be calculated as the row total times the column total divided by the grand total. So let's see how this works. So we can do a test. We'll compare those observed and expected values with a chi-square test, of course. Now, the row and column totals constrain the degrees of freedom, so we're going to have to subtract off a little bit more than 1. In fact, the degrees of freedom is rows minus 1 times columns minus 1. And so here's our usual chi-square statistic. Okay, so count minus expected value squared divided by expected value. Add them up over all the rows and columns, and then you get a chi-square distribution with those indicated degrees of freedom. So sum over all rows and columns. All right, so let's look at an example. Now I've calculated most of the expected values for us here. Fire department in a large city is examining its promotion policy for possible age discrimination. They sampled 248 promotion decisions and cross-tabulated them by age and promotion decision. So we see that we've got 4 age categories and then promoted or not. The numbers, the first numbers are the actual observed values. The numbers in parentheses are the expected values. And this is pretty common notation. You'll see this in a lot of textbooks. I've calculated all but one of them. Here's a typical calculation for, let's see, row 2, column 3. So I took 164 times 80 and divided by 248, and that gave me the 52.9 number. I calculated all but one of them and you'll show you in a little bit later example that maybe I didn't really need to calculate even that many. But I calculated all but one, and I want to show you a trick. When I get down to only having a few left, I need not do this multiplication because the numbers, the counts, have to be conserved, whether it's observed or expected. So if I subtract this expected 16.9 from 50, then what I'm going to get is 33.1. And that'll keep the balance in the rows and column totals. Now I go ahead and calculate degrees of freedom. So two rows, 2 minus 1 is 1. 4 columns, 4 minus 1 is 3. So I have 3 degrees of freedom. Oh, put the answer right there, didn't I? If I look this up in the chi-square table, at the 5% level, the critical value is 7.81. And if I go ahead and actually do the calculations, I'll get a chi-square statistic of 12.8, which exceeds the critical value. So I'm going to reject the null hypothesis. They're not homogeneous. So possible discrimination. Age discrimination. So somebody's got some work to do. Now, if you don't want to do this stuff by hand, you can go into R. You can go into R and use the chi-square test. And so what you're going to do is set up a matrix of values that's got all the observed counts and make sure that it comes out as a 2x4 matrix, and then just do a chi-square test on it. Now the other test we can use is a test of independence. Independence talks about random events. Not separate samples. So the example here is one that's near and dear to most people who've studied genetics, Mendel and his peas. And so Mendel did a huge number of experiments crossbreeding sweet peas and recording characteristics, trying to figure out relationships and basically coming up with the whole idea of crossbreeding and alleles long before genetics was ever invented. So here's one of his experiments where he looked at a cross of green peas and tried to look at the relationship between color and shape for the peas. So he had 2 different colors, yellow and green, 2 different shapes, round peas and wrinkled peas. He had 556 plants, and he was able to cross-tabulate them into these 4 different categories. And then the question was, are these two categories, or these two random attributes, independent or dependent? Okay, so a large chi-square statistic would indicate that they're not independent. A small one would indicate that they are. I went ahead and calculated the expected value for the very first cell, round peas that were yellow. And the expected value is 316.5. Now, let's use the great degrees of freedom trick. So peeking ahead, we see that the degrees of freedom is 2 minus 1 times 2 minus 1 is 1. So that's my degrees of freedom. And so now let's look and see what that implies for this table. Well, if I know the round yellow count, expected count is 316.5, and I subtract that from the row column total, I'm going to get 99.5. If I subtract that from the row total, I'm going to get 106.5. And now, using those, if I take the 106.5 from the 140, I'm going to get 33.5. That is, I only needed to calculate this one, use row total, let's see, times column total over grand total. So I only need to do that for that one, and then degrees of freedom and subtraction basically allows me to calculate all the rest. With 1 degree of freedom, the chi-square statistic at 5% level is 3.98. So let's go ahead and calculate the test statistic. So 315 minus 316.5 squared over 316.5, and then 108 minus 106.5 squared over 106.5 plus 101 minus 99.5 squared over 99.5 plus 32 minus 33.5 squared over 33.5. And after beating on it with a calculator for a little bit, I get a test statistic of 0.0118, which of course is much, much less than the critical value. So do not reject H naught. They appear to be independent. Again, here's how you'd set that up in R. So set up a matrix of values with 2 columns. Notice that R does things in column major order, so this is going down a column and then down another column. And then just do the chi-square test. Wait a minute, we use the same test to test for 2 different things? Yeah, that's possible. Means it's a good test. For homogeneity, the characteristic strata are fixed, like the promotion decision, okay? For independence, both characteristics are random, like color and shape. And unfortunately, the chi-square test handles them both. Pretty neat, huh?